again introduce the autocorrelation coefficient and its role in identifying the structure of a time series process. If we recall, the basic expression for autocovariance for a time series process yt at lag s was expectation of yt minus expectation of yt into yt plus s minus expectation of yt plus s, which is denoted as gamma s. This gamma s is autocovariance at different lags of 0, 1, 2 and so on. When this s equal to 0, the autocovariance at lag 0 is obtained, which is simply nothing but the variance of yt itself, which can be denoted as gamma naught. One problem with these autocovariances is that they have different units of measurement if you are measuring the different process, and therefore it is difficult to compare and interpret them directly because of this scale issue, and therefore a good way is to scale or standardize them with the variance gamma naught. So if you believe the process has a constant variance, that is gamma naught, which is nothing but the autocovariance of a process with its self, that is yt at s equal to 0, which means this will also become yt. This becomes variance term, and assuming if for a process variance is constant, that is gamma naught, if I divide any autocovariance gamma s with gamma naught, it is called autocorrelation measure tau s, as we have seen earlier. Now this tau s has a very interesting property that it lies between -1 to +1, where -1 means completely opposite movement, opposite lockstep movement, while +1 means completely in one direction. Generally in life, in practical scenarios, the number will be somewhere in between. Now, what is the importance here? Before we explain the importance, one thing you noted, as s equal to 0, tau s becomes tau 0, which is nothing but gamma naught upon gamma naught equal to 1. So the autocorrelation of a process with itself contemporaneous term is 1. Now, generally for a white noise process, and assuming, and recall we said that we generally tend to assume that it's a normally distributed white noise process. So a white noise IID process with a normal distribution which has no autocorrelation structure, if you simulate the autocorrelations tau s, they are approximately, that means in large numbers, if there are large number of observations asymptotically, they are normally distributed. So for a white noise normal IID process, the autocorrelation themselves will be asymptotically, that means with large number of observations are approximately normally distributed with a mean of 0 and a variance of 1 upon t. That means if we plot it, it will appear something like a normal distribution, a bell-shaped curve with a mean 0 and a variance of 1 by t. Now, with using this property, we can set up a confidence interval for any such process where we want to establish whether there is some autocorrelation structure or not. So for example, if you believe that a process is a white noise process and you plot it on a standardized normal distribution, which is nothing but a standardized version of normal distribution, its mean will be equal to 0 again. And now with 95% confidence interval, which is nothing but almost 2 standard deviation, on normal distribution this point will appear at z equal to minus 1.96 and this is plus 1.96, and on a absolute simple normal distribution this will be minus 1.96 into sigma, which is 1 upon root t. Variance is 1 upon t, so standard deviation is 1 upon root t. Similarly, this upper limit of that 95% confidence interval be plus 1.96 into 1 upon root t. So we can set up this confidence interval, and if there is no, I repeat, if there is no discernible structure, there is no autocorrelation, then the 95% confidence interval will be this. And if your observed sample correlation is beyond this range, that means either on the left side of the rejection region or on the right side of the rejection region, then you can with 95% confidence say that there is indeed some kind of autocorrelation in the process. Similarly, you can set up 99% or any other confidence interval using the corresponding Z values. So in summary, we are saying that as long as we are setting this 95% confidence interval with the assumption that process is a white noise IID process, that means there is no discernible structure, you can reject the null if your sample autocorrelation tau s lies outside this region for a given lag s, and that would indicate the rejection of null hypothesis. That means if the correlation is outside this region and you are able to reject the null, which would suggest acceptance of alternate HA, in general we call alternate as HA hypothesis, that there is indeed a significant, I repeat, significant, or what we call as non-zero coefficient at lag S. Now whether that coefficient is positive or negative, that will depend whether you reject in this tail or the right tail. If it is rejection in right tail, then probably it is positive, non-zero positive. If it is on the left tail, then it is non-zero negative. Now there are two advancements in this statistic. One is called Box-Pierce test statistic, which is Q equal to T, which is the sample size, into tau k squares, the summation of all the correlation coefficient squares, and LB test, Lung-Box test, which is called Q star static, which is nothing but T into T plus 2 and then tau k square summation upon T minus K, where tau k is your autocorrelation coefficient at lag K. Now, these two are slightly different from the previous hypothesis or confidence interval estimation of autocorrelation coefficient. In the previous case, we were testing autocorrelation coefficient at different lags individually. These are joint tests of autocorrelation coefficient. That means when I run this test for Q or Q star, essentially I'm testing that up to the lag K, up to this lag K, all the coefficients are jointly equal to 0. I repeat, the null hypothesis here is that all the coefficients up till lag K are 0. The rejection of null, that is acceptance of HA, will indicate that at least one of them is significant. So these are slightly more powerful tests. The statistics are asymptotically distributed as a chi-square statistic. So you pick up the relevant values from the chi-square, this chi-square table, and compare them with the Q and Q star, and depending upon whether Q and Q star are higher or lower than these statistics, you reject or accept the null. So we'll see some of the examples in next set of videos. Notice if T is sufficiently large, then both of these statistics, they converge towards the same value. That means Q star and Q tends to become same. They converge towards each other when T is very large and increases towards infinity. Now, to summarize, what is the application or important role of this autocorrelation coefficient? The idea here is that the good idea here is that when you model any process, any time series process through models such as ARMA model, and extract the residual out of it, muties, those residual, you tend to assume as a null hypothesis that these residuals are normally distributed. They are like a white noise process with a normal IID distribution, that means independent and identically distributed with a normal distribution. However, then you apply these kind of null with either individual hypothesis test that we did in the previous discussion, or now with Q and Q star statistic, and you are able to reject the null that there is no autocorrelation. Then you have to conclude that there is some autocorrelation structure, and then probably your modeling of process was not a very good fit. And that is the whole point of it, to find this autocorrelation structure in the process, whether there is some discernible structure and your error terms indeed are not white noise. If they are not white noise, then the model that you have fit to, you model original process YT, because YT was your original process which you fitted with some kind of ARMA or some model to obtain these error terms. That original model parameters were not very appropriate, or model itself was not very well specified, and you need to relook at your modeling exercise. That is the conclusion with this. So to summarize this video, we have introduced again autocorrelation coefficient, and we also saw their application in modeling time series processes. Please note, when you plot these autocorrelation coefficient on x-axis with different labs s equal to 0, 1, 2 and so on, this kind of diagram is called autocorrelation function, or ACF, or correlogram when you plot it visually across lags. Now that we have understood the theoretical underpinnings of autocorrelation coefficient, we'll try to explain its working and application with the help of a simple example. Consider a simple experiment or examination of a process YT where you have 100 observations, and at lags 1, 2, 3, 4, 5, you observe the following correlation coefficients. First order coefficient tau 1 as 0.207, tau 2 as minus 0.013, tau 3 as 0.086, tau 4 as 0.005, and tau 5 as minus 0.022. You want to test first individually whether these correlations are indeed statistically significant, that means non-zero, by that confidence interval approach. That is this setting up this 95% confidence interval and checking each of the correlation coefficients individually whether they are non-zero and statistically significant. And the second joint test or joint hypothesis approach with Box-Pierce BP and Lung-Box LB test, to conduct the joint hypothesis whether all of them together are significantly or non-significant or equal to 0. Let us start with the simple 95% confidence interval approach, where we would like to set up a plus minus 1.96 into 1 upon under root t confidence interval like this. So you want to set up a confidence interval like this upon under root t and plus 1.96 upon under root t, and want to test whether each of the coefficient lie outside or inside this range. Because t here is 100, this number works out to plus minus 1.96 upon 10, which is minus 0.196 to 0.196. So this range is minus 0.196 and this range is 0.196. Now if we compare our coefficients individually one by one, let's see. So by that logic, this coefficient 0.201 is significant, this is not significant, this is not significant, this is not significant, and this is not significant. So that means only one autocorrelation coefficient at lag 1 is significant and non-zero, and this is positive also. So this is what we conclude from the first test. Let's look at the joint test. In the joint test, our null hypothesis is that all of them, tau 1, tau 2, tau 3, tau 4 and tau 5, all of them are jointly equal to 0. And now we would like to compute the statistics respectively q and q star with these formulas. T here is 100, all the tau k's are given, tau 1, tau 2 and tau 3, tau 4, tau 5 are given to us, and it is given to us that statistics corresponding to 5% significance or alternatively 95% confidence level is 11.1, and at 1% significance, that is 99% confidence, is 15.1. So let us work out the numbers. So if I compute the box-Pierce statistic, that is t into summation of all the squares of autocorrelation coefficients, t is 100 and all the individual coefficients are shown here, their squares are added up, we get a value of 5.09. Similarly, Lung box or LB statistic is also given to us, which is 100 t into t plus 2 and into that formula tau k square upon k minus 1 k minus t minus 1 t minus 2 and so on up till t minus k works out to 5.26. Now if you recall, our statistics at 5% and 1% level, none of them are significant. That means whether I compare with 5% or 1%, both the statistics are insignificant. What do we conclude here? In both cases, with the help of joint null hypothesis that all of them are 0, we fail to reject the null. That means we do not accept the alternate, and we conclude that all the coefficients are equal to 0 cannot be rejected. So we have to take them together as non-zero. However, this is in contrast with the first confidence interval approach, where the first coefficient of 0.206 appeared to be significant individually, while others were non-significant. So why this kind of contrasting result? So to summarize or conclude, here what is happening is that at lag 1, the coefficient is pretty large, it's 0.206, which is significantly different from 0. However, when we conduct the joint hypothesis, that means all of them, whether all of them are equal to 0, given the small magnitude of these tests, that for example tau 2, tau 3 and so on, these are so small that the overall power of joint test is decreased because of the smaller coefficient, and they go in favor of null. I repeat, because of the small magnitude of these coefficient, the overall power of test is pretty low, and we have to conclude when we conduct the joint hypothesis, we have to go ahead with the null that all of them are together equal to 0. But when we examine them individually, clearly the first lag autocorrelation coefficient is pretty large, and we have to conclude that this process has a significant first order autocorrelation. So for example, if you try to put this process on some kind of AR process, it will be an AR1 process. It will be an AR1 process with this kind of structure into yt minus 1 plus our error term. Now here mu is almost 0. We'll consider mu to be 0, and this kind of process will appear. Mu t is this is error term, which is generally a white noise process. So you can consider this error term, and the process will appear like this. We'll introduce autocorrelation function and partial autocorrelation function and understand them with the help of AR process, and how to differentiate AR process with the help of ACF and PACF diagrams. To begin with, we have already understood that autocorrelation function or correlogram is a plot of these autocorrelations across different lags starting from 0, 1, 2 and so on. and that this autocorrelation function at lag 0 takes a value 1 and then subsequent lags it takes different values. However, the problem is that because the process is correlated, for example, there is some kind of correlation between yt and yt minus 1, if even if there is a single order correlation, that is some correlation phi between yt and yt minus 1 and yt and yt minus 1 and yt minus 2, there is a spurious correlation. Mathematically, there is a spurious correlation that results between yt and yt minus 2, which is smaller than phi, somewhere around phi into phi, closer to phi square, driven by the fact that there is a correlation between yt and yt minus 1 and yt minus 1 and yt minus 2. So closer to phi square kind of correlation appears between yt and yt minus 2 and phi cube between yt and yt minus 3 and so on. And therefore, if I want to know the exact autocorrelation structure, I need to go with something called PACF, partial autocorrelation function, which accounts or sort of accounts for this spurious autocorrelation and gives me a pure correlation, pure autocorrelation across different terms, let's say phi t to yt minus 2 or yt to yt minus 3. Now, how does an AR process figure on these ACF and PACF grams? Conceptually, when you have a autocorrelation structure, the AR process has a geometrically decaying ACF. I repeat, AR process has a geometrically decaying ACF because of that spurious correlation. However, the PACF process accounts for this spurious correlation and only shows the exact autocorrelation structure that is present, and therefore on PACF diagram you have non-zero points only equal to AR order. For example, if your actual autocorrelation structure is of 2 lag, that is with lag 1 and lag 2, then PACF will have 2 non-zero points at lag 1 and 2 and rest of all will have 0 values. Let's look at how it appears. We have a simple AR1 process with first order autocorrelation of 0.9. So the dark blue bars are ACF, and notice it takes a value of 0.9 at first lag, but second lag it is closer to 0.81 and then 0.89 cube and so on. So kind of exponentially declining structure with ACF diagram. As we discussed, so these rest of these, the first autocorrelation is correct, but rest of them are spurious. So how PACF accounts for it? Let's look at the lighter blue diagram, lighter blue bar, which is PACF. The first bar at first lag is exactly identical as the ACF diagram, but then it is cut off there itself. Then there are no lags. So that means PACF diagram clearly helps us identify that this is a first order autocorrelation structure. Similarly, look at this AR1 process where first order autocorrelation is 0.5. Again, the first lag at lag 1, we have ACF and PACF values are non-zero and same as 0.5, but then ACF exponentially declines while PACF the values are straight away cut off to 0. So in this fashion, PACF helps us in identifying AR process. Please note that if there were two AR terms, they will be appearing on PACF process in the form of 2 bars and so on for 3, 4 and more autocorrelation structure. But on ACF, they appear as exponentially declining bars. Let's look at another 2 diagrams. Interestingly, in this we have AR1 process with a negative autocorrelation structure. So first at lag 1, we have a value of minus 0.5, which is same for PACF and ACF both, this PACF and ACF. However, after that, you notice that it takes minus 0.5 to the power 2, which is close to 0.25, and therefore magnitude exponentially declining, but sign is continuously changing with the power of minus 0.5 to the power n, depending upon n first, 1, 2, 3 and so on. This value, the bar is positive or negative, but on PACF there is only one bar, which is first lag minus 0.5. Again, PACF helps us in identifying the AR process, its lag structure. If you look at a non-stationary process, notice this is a non-stationary process because here the autocorrelation coefficient is 1. So it is on the unit root circle. And notice on ACF diagram, because of this property that shocks are not declining, it's a non-stationary process and shocks are not decaying. On ACF diagram, we have continuously all the bars at 1, including 1, 2, 3 and all the subsequent lags. However, again on PACF, the bar is only non-zero and takes a value of 1 at first lag and then it is cut off. So this identifies the process non-stationary because now the ACF bars are non-declining, they are constant, which shows non-decay. There's no decay of shock, which is sort of indication of a non-stationary process. But PACF, again, we can identify that non-stationarity appears at first lag with the order of 1. So to conclude and summarize, in this video we saw how with the help of ACF and PACF process we can identify AR process. So when we look at AR process, its ACF is geometrically declining for a stationary process and PACF has exactly non-zero lags which are same as the order of the process, AR process. We'll introduce another very important class of time series processes called moving average processes or MA processes. This form that in ARMA model, that MA component, moving average process, a very important component of ARMA model. Let us introduce the model and concept behind the MA process. Think of a financial time series process YT such as security market returns as a linear combination of error terms or white noise processes called mu-t. So here the concept or idea behind this process YT is that it is simply a linear combination of these white noise, the current white noise terms mu-t and historical white noise term mu-t minus 1. So what are these mu-t's? Conceptually, these mu-t's are like information shocks that have arrived in the process at time t. Think of day t, let's think t in terms of days, and any sentiment or information shock that has arrived on day is modeled as mu-t. Now, a white noise process mu-t with a sort of zero mean, that is expected value of mu-t as 0, and a constant variance sigma square, the variance of mu-t as sigma square, are employed to model this mu-t term. Generally, it is believed that information that is arriving has no connection with its own self previously or historically. For example, the information that has arrived today probably may have no relation with information that has arrived tomorrow or yesterday. That is one assumption which leads us to employ white noise processes, a very important assumption. And second, we also assume there is no discernible structure. So the correlation terms across mu-t's, mu-t minus 1 and so on up till mu-t minus k, there is no discernible autocorrelation structure, and that leads us to model this mu-t process simply with the white noise as a white noise process. Now please note, while we are assuming it as a white noise process, in financial and economic terms, this mu-t for us is some kind of information shock that has arrived on date t, and we tend to assume it to be a closer associate of a white noise process. Now let's again go back to our MA model of process YT, which is a linear combination of these mu-t's, current shock mu-t and historical shocks mu-t minus 1. Mu here is the average, some kind of average value or constant value. For practical modeling purposes, later on we'll consider this mu as 0. So this constant term is 0. Let's take 30 seconds to understand what this constant mean is. This constant mean for a process like security market return is average return, average period by period return. Now, if you're talking about financial market and a stock gives you a fixed abnormal extra average period by period returns, that sort of violates the concept of market efficiency, and therefore for all practical purposes this number should be very close, insignificantly different from 0, and therefore we may take it as 0, and that will help us ease the mathematical modeling part of the process as well. So let's begin this assumption that this mu is very close to 0, and all we are interested in is modeling these current and historical shocks or white noise processes, mu-t, mu-t minus 1 and so on, and theta 1, theta 2, these thetas being the correlate sort of coefficients of these shocks. Now we can again put it in a sigma in a more compact manner with the help of lag operator. What is a lag operator here? So again, as we discussed, a lag operator, something Li of YT process is nothing but YT minus I at ith lag. So if I'm writing Li of mu-t, it is like mu-t minus I. So this is often referred to as either lag operator or backshift operator. So we can start from this notation to a more compact sigma notation like this, where sigma equal to 1 to q, theta I into mu-t I minus 1, where I runs from 1 to q, and later on we can apply a lag operator, a lag function of theta, like theta L mu-t, where theta L is nothing but 1 plus theta 1 L for plus theta 2 L square and so on up till theta q L q. Now these algebraically, this polynomial, this can be considered as a polynomial. For example, second lag L2 with Volt's theorem can be taken as L square, and we'll make use of it algebraically. And please recall, in our previous videos we said for AR process this was characteristic equation for the AR process. In that case, here we'll consider it as a characteristic equation of moving average process. Last, another very important point, while modeling this, we have taken mu-t's to be white noise IID terms that are distributed with a zero mean and constant variance. For ease of modeling, we take the distribution at which they are distributed as normal. So this IID, or independently identically distributed mu-t's, are taken as normally distributed. And to summarize, a moving average model is simply a linear combination of these white noise mu-t's processes of current time and historical times. Once we have finalized these assumptions about the MA process, we can derive certain useful results. So look at this mu-t process or time series MA Q order process. So these mu-t's run up till time like Q. This is considered as an MA process of order Q. There are some desirable results. The expected value or the mean or this process is mu. Again, this will become 0 for us while later on when we are modeling these results. But still, theoretically, this value is mu. But in financial markets, this will be taken as close to 0. The variance of mu-t is this constant number, which is a function of the variance of sigma square, which is the variance of mu-t itself, and summation of these theta 1 square, theta 2 square, which is nothing but the coefficient of these mu-t's. So this is a constant value driven by this expression. This is also called gamma naught, the variance term. What about autocovariances? So this was variance. Autocovariances are also given by this expression. As we can see, theta s plus 1 into theta 1 and so on. And then a multiplication with variance of the sigma square. What is the sigma square here? This is the variance of mu-t. We assumed a constant variance of mu-t white noise processes. These white noise processes are constant variance for different lags, t minus 1 and so on, as sigma square. So this is also same as, this is one critical assumption. Slightly it may change. So there's nothing that forces this assumption to hold. It's just a simplifying assumption to make modeling easy. And also please notice, these autocovariances will exist maximum up to order Q. So because we have considered an MA process of order Q, these autocovariance structure will start from lag 1 and up till lag Q. So the Qth lag will be the last lag by which autocovariance will exist. After any lag higher than lag Q, autocovariances will be 0. So to summarize these notation, what we can call about this MA process, how we can summarize this MA process, as for a MA Q order process, it has a constant mean mu, a constant variance, this one, which also depends what is the order of the process theta q, and autocovariances that are non-zero up to lag q and 0 thereafter. So up till lag q they are there and 0 after that. So now we have understood the concept and mathematical model behind the MA process. In next set of videos, we'll try to work out some of these MA process with the help of simple examples. We'll understand the MA process modeling with the help of a simple MA2 order process. Let us define a simple MA2 order process like this. YT as a combination of white noise processes mu-t minus 1, mu-t minus 2. These are the two previous period shocks. That's why second order process, MA2 order process. And theta 1, theta 2 are the coefficients of this white noise process, where expected value of mu-t equal to expected value of mu-t minus 1 and so on, expected value of mu-t minus 2 equal to 0. So it has 0 expected value, and its variance of mu-t is equal to variance of mu-t minus 1 equal to variance of mu-t minus 2 equal to sigma square. So this is assumption about white noise process, and we take it to be a normal, some kind of normal white noise process. So what is the expected value or unconditional, some kind of mean of YT as expected value of this expression, which is nothing but this. Now expectation operator runs on stochastic variable like mu-t. For constant, it is for example, expected value of theta 1 would be theta 1 itself, because it's a constant term. So we apply expectation operator one by one. So expectations of mu-t plus theta 1 times expectation of mu-t minus 1 plus theta 2 times expectations of mu-t minus 2. But these expectations are nothing but 0, because we already said we have assumed this is as a white noise process with a 0 mean. And recall, for YT itself, we are using that constant term mu as 0. Like I said earlier in the previous videos, we'll take that constant mu as 0, which that's why I have not put that mu in that MA process here. the mean term or constant term, and remaining all these mu t's, their expectations are 0. So we get the expected value of yt as 0. This is our generic expression for white noise processes with MA 2 order yt, its expectation is 0. Let's come to the variance part of yt. Now variance of yt, the generic expression is expected value of yt minus expectation of yt into yt minus expectation of yt, because this is a variance part. Now please note, expected value of yt is already 0 that we have defined here, so we'll simply substitute this for 0 and we get expected value of yt into yt, which is expected value of yt square, and we can now put yt, we can substitute this value of yt here and here. If you focus on this expression, you would notice that there would be some square terms. When mu t gets multiplied with mu t, you will get mu t square, or mu t minus 1 multiplies with mu t minus 1, you'll have theta 1 square mu t minus 1 square, and similarly you'll have theta 2 square mu t minus 2 square. But then there'll be some cross product terms when mu t gets multiplied by mu t minus 1. However, and the catch-all expression for these cross product terms is this, and if you recall, we said that this mu t is a sort of white noise processes. So therefore any correlation between mu t and its previous lag, like mu t minus k, for k equal to 1, 2, 3 and so on, will be 0. So what I'm essentially saying is that correlation or expected value of mu t into any mu t minus k, this can be mu t minus 1 or mu t minus 2, all these terms, the catch-all expression will be 0 with a simple financial logic, and here financial economics dominates over mathematics, that there is no correlation, there is no discernible structure or correlation across mu t's across different time periods, and therefore the catch-all expression for this term is 0. And we are left with expected value of mu t square as this part only. So the remaining, for all the cross products, the expectation is the expected value of mu t into mu t minus 1 is nothing but covariance of mu t and mu t minus s, which is 0. Why? Because we said that mu t's are white noise processes with no discernible structure, and therefore no autocorrelation or covariance. And therefore all we are left with this expression. But here we also said that this expectation of mu t square is by definition nothing but covariance of mu t. This covariance of mu t comma mu t is nothing but variance of mu t, and which is same as sigma square. So we have already defined that expectation of mu t into mu t is nothing but covariance of mu t with mu t itself, which is nothing but variance of mu t, which is equal to sigma square. And whether now it is mu t minus 1, variance of mu t minus 1, or mu t minus 2, all of them are sigma square. So with this logic, we are left with this expression, and knowing that this is sigma square, this is also sigma square, and so on, we can take this sigma square common, and because theta 1 square, theta 2 square are constants, their expectation, for example, expectation of theta 1 is same as theta 1, and expectation of theta 1 square is also theta 1 square, and likewise for theta 2 and so on. So this expression, that is variance of yt, is nothing but 1 plus theta 1 square plus theta 2 square into sigma square. This is simply because this is a MA2 order process up till theta 2 only. So we have up till theta 2. If there was a generic term theta k, as we saw in the previous videos, it will go up to theta k square. So now we have obtained the expressions for expected value of yt, which is 0, with the assumption that this process yt itself has no constant mu term, which we assume to be 0, and therefore our modeling part has become much easier with the expected value of this MA2 order process as 0. First very important result, and second very important result, the variance of this process is 1 plus theta 1 square plus theta 2 square into sigma square. So the variance term is also dependent on these coefficients theta 1, theta 2, and the variance of this white noise process mu t, which is sigma square. So now that we have understood the variance and expected value of this MA2 order process, in the next video we'll look at its autocovariance. We'll try to understand the autocorrelation structure of MA2 process. Recall, in the previous video we have tried to compute the variance of an MA2 process, this kind of process. In this process, we had considered a constant mean, which is 0, and these two terms define this MA2 nature of the process. Now, for this process, let's start with the basic definition of autocovariance at lag 1. So that is expected value of yt minus expected value of yt into yt minus 1 minus expected value of yt minus 1. We have already said in the previous video that expected value of yt is same as yt minus 1 and so on for 0 for this particular given process, and therefore these terms will become 0. So we are left with expected value of yt into yt minus 1. Now again substituting for yt this expression, and for yt minus 1 which is just 1 lag previous, so we'll have instead of mu t we'll have mu t minus 1, instead of mu t minus 1 we'll have mu t minus 2 and so on up till mu t minus 3. Now if you recall the multiplication of mu t into mu t minus 1 or mu t minus 1 with mu t minus 2 and so on will lead to cross product terms, while multiplication of mu t with self, in this case there is no mu t, so we have mu t minus 1 into mu t minus 1 leads to square terms. If you recall from the previous video, given that these mu t are white noise process with no autocovariance, all such cross product terms, the catch-all expression for all such cross product terms is 0, and only those terms that are variance, that is mu t minus 1 into mu t minus 1 or mu t minus 2 into mu t minus 2. So mu t minus square minus 1 and mu t minus 2 square will remain. Their coefficients are easily determined. For example, mu t square minus 1 is a combination of this and this, so it's theta 1. Mu t minus 2 will have theta 1, theta 2 and so on. So this is the expression for autocovariance gamma 1. Or we already know that expected value of variance of mu t minus 1 and mu t minus 2 is same as sigma square, so we can take that out. So this is the expression for autocovariance at level 1. What about level 2? So for level 2, this t minus 1 will become t minus 2, t minus 3 and t minus 4, and now only these two terms will survive. So we'll have theta 2 times sigma square. All the other terms are cross products, like for example mu t minus 1 and mu t minus 2, mu t minus 2 with mu t minus 3 and so on. So this is gamma 2. If we move anything ahead, if we move any further than second lag, notice this will become mu t minus 3 and therefore and this mu t minus 4 and mu t minus 5. So all the products will become cross products. There will be no variance terms, and therefore the value for gamma 3 or autocovariance at lag 3 is 0. What is causing this? This is precisely driven by the nature of this process, which is MA2 process, because there is no theta 3 corresponding to mu t minus 3. This is only two second order process. The third variance, the autocovariance at third level is 0. So we are restricted for autocovariances at level 2. Similarly, had it been an MA3 process, there would have been term for gamma 3, that is autocovariance at third lag, but no fourth lag and onwards. In the next step, we'll compute the autocorrelation function ACF or taus. So these tau i's are nothing but autocovariances divided by variance terms. Variance terms we have already calculated in the previous expression as this. For this process, this was our variance term. So let's start with tau naught. Tau naught, as we already know, is nothing but gamma naught divided by gamma naught, that is variance divided by variance, and it is 1. So irrespective of the process, this will always be 1. But what about tau 1? Tau 1 is gamma 1, which is autocovariance at lag 1, which we have computed in the previous slide like this, and gamma naught we have already computed in the previous video like this. So this will cancel each other out and we are left with this, which is tau 1. Similarly, I can calculate tau 2, which is gamma s upon gamma naught, which is this expression. There is no tau 3. Tau 3 is equal to 0 because precisely this was MA2 process and any further correlations would be 0. So to summarize, in this video we understood how to compute autocovariance, and with those autocovariances dividing them by variances, how to compute autocorrelation functions tau naught, tau 1, tau 2 for this MA2 process. We also noted because this was MA2 process, any higher order autocorrelations and covariances would be 0 because the process is restricted to second order lag of muties. We'll try to understand the autocorrelation function and partial autocorrelation function, that is ACF PACF plots for an MA process, and differentiate it with AR process. To begin with, recall in the previous video we said that MA process has an autocorrelation function or ACF, which is exactly the number of autocorrelations or the number of white noise terms, the order of MA process, which is same as order of MA process. So the number of autocorrelation terms tau i's will be significant, which is equal to exactly the MA order. In the previous case, it was second order process, so we had autocorrelation functions tau i's significant up to second order. So that clearly explains that when we'll examine the ACF, it will be the number of ACF or autocorrelations will be same as MA order. But what about PACF? Without going into the mathematical proof, theory suggests that an MA process can be transformed into infinite order AR process. I repeat, an MA process can be transformed into an infinite order AR process, and therefore when it is examined on the PACF plot, there will be infinite number of correlations for an MA process. And therefore, when we examine ACF for the MA process, for example, look at this MA process, which is a simple first order MA process with the coefficient as minus 0.5 for the white noise mu t minus 1. So if you look at ACF, which is in dark blue, it is cutting off at the first level itself. Only there is one bar which indicates that this is a first order MA1 process. However, if you look at PACF, their magnitude is exponentially declining. So the magnitude of PACF is exponentially declining through a reasonable number of large terms. So it's like exponentially declining. Similarly, if you look at this MA2 process where one term is positive and another is negative, 0.5 and minus 0.5, we look at the dark blue has two specific, the ACF has specific 2 bars, while again the magnitude of PACF is exponentially declining in terms of graph, positive negative, which reflects this kind of structure, positive negative, but in terms of magnitude, the magnitude is exponentially declining. So this is how we interpret the ACF and PACF plots for MA process. If to summarize, if we contrast these ACF, PACF with the AR process, recall for AR process, the ACF diagram was exponentially declining while PACF was exactly cutting off at the number of bars same as AR order of the process, ARQ then order Q. In contrast, for MA process, the number of ACF bars are exactly limited to MA order. So if it is MA P order process, the number of bars in a ACF diagram will be P. However, if you look at the PACF plots, they will be exponentially declining in terms of magnitude because, like I said, an MA process can be converted into infinite AR process, and PACF will represent that characteristic that the number of lags will be exponentially declining. That infinite AR kind of process. Obviously, that infinite AR process has coefficients that are declining as we go ahead and pass. So this declining nature will be captured in the PACF. That infinite AR process will be captured with these PACF diagrams. So this is how we different and contrast between AR and MA process on ACF and PACF plots. To summarize, we noted that time series models offer an extremely simple and useful class of models. In particular, we noted that time series processes are effectively modeled with ARMA processes. However, any time series modeling requires a stationary data, that is a constant mean, constant variance, and autocovariance structure that is not changing across time. We also noted that a non-stationary property has a very undesirable property that its estimation results in spurious relationships that do not exist. Then we introduced autoregressive or AR processes, which are a very important class or component of ARMA models. In the AR process, a time series is expected to be dependent on one or more of its own past values. An ARP process is said to have an order P, that is, the series is dependent on its own past P values. The strength of this relationship is defined by the autocorrelation coefficients of the process. Moreover, if the series is stationary, then these autocorrelation coefficients have a declining structure. That is, they tend towards zero as we go back in time. This is a desirable property as it indicates that the impact of distant terms is less in magnitude. A stationary AR process can be identified with the help of one exponentially declining ACF plot and two a PACF plot that has non-zero bars up till the order of AR process and no bars, that is zero thereafter. An MA process is a linear combination of current and past white noise error terms. An MAQ process is said to have an order P if it is dependent on its P historical values. An MA process is said to be invertible if the coefficients of white noise terms have a declining structure as we move further down in past. Also, then it can be converted to an infinite AR process as well. A white noise process has no discernible structure, and MA process can be further identified with an exponentially declining PACF diagram and an ACF plot that has a non-zero bars up till the order of MA process and no bars, that is zero thereafter.